Thanks for coming to my talk. I know it's pretty heavy competition with Von Vernon going on next door, but this one's better. My name's Doug McPherson. When I submitted this talk, I worked for AirHop Communications, which is a startup out of San Diego. We were Lightbend subscribers, and very happy Lightbend subscribers, and I was so impressed with Lightbend that I joined the company. So now I'm a member of Lightbend. The good folks at AirHop gave me permission to give this talk anyways, so this is all about the project at AirHop and doesn't really reflect necessarily Lightbend views, but of course the reason I'm here is because we were using Lightbend tech. So the subject of the talk is how we use Akka to optimize your device's network. And I'm talking about wireless networks, cellular LTE wireless networks. And just so we're all on the same page, just review really quickly the cellular concept. So you have a mobile device, such as a cell phone, and he needs to be in radio frequency communication with a base station. Base stations come in all shapes and sizes. This cell phone is currently nicely connected to this base station, this black base station, with a good signal, and the user's happy. And as he moves geographically through the region, he stays connected, and from time to time he may get closer, by some definition, to another base station, and he does what's called a handoff. And as he continues to move, he's still happy because he's still connected, and he may continue to move. But then, if the network's not set up properly, and there's a million things that can go wrong, the call drops because he's too far away from a neighboring base station, and things don't resolve themselves until he moves a little bit further. So that really is the basic problem with cellular communication. And there are, as I said, there's a million things that can go wrong in here, and that's why cellular networks are so complicated. The RF environment is extremely harsh. Signal degradation due to, of course, obviously distance from the transmitter, but also terrain, buildings, other structure, leaves, weather, all those things get in the way and make the transmission of your signal or reception of your signal more difficult. One of the worst problems is known as multipath scattering, where the signal is transmitted from the base station, but before it reaches your device, it bounces off several buildings or other structures, and it arrives at your device, and the signals are, they're RF waves, and so they can have constructive and destructive interference. The destructive interference, of course, is the really bad one, and you can get what's called fast fading due to this, which is fades that are relatively quick, but quick by some definition. They can last for maybe 40 milliseconds, but they can be as deep as 40 dB down. So that's a difficult problem to have the signal drop by that much. The other thing that happens with multipath is that all these different copies of the signal are taking different paths to get to your device, and that can tend to smear the actual signal out in time, and this is called delay spread. With certain cellular systems, especially LTE, neighboring base stations are using the same frequency, and so you're actually fighting with interference from neighboring base stations. And so that's another thing that is that we try to mitigate. The resources are scarce, so the radio frequency spectrum is limited, and it's expensive. It's expensive because it's limited. Power consumption must be minimized, especially at the device, meaning at your phone, for obvious reasons. You want your battery to last all day. The base station itself will support a finite number of users for large base stations that can be, around 512, perhaps less, but possibly as few as 8 users for really small base stations. So what all this means is that as the demand for cellular service increases, the number of users increases, and their demand for data rate, for capacity increases, the cells have to be shrunk. In other words, they serve smaller areas so that the number of users that they encompass are fewer, and so they can continue to offer the data rates that people are demanding. So another thing that is at play here is customer experience always needs improvement. So the wireless carriers are trying to minimize drop calls, increase data rates, and eliminate coverage holes so you don't get that X right in the middle of an important conversation. Another thing, of course, that operators are trying to do is reduce operator capital expenditure and operational expenditures. There are hundreds of parameters between the base station and the device that can be adjusted, or dials that can be turned in order to achieve optimal performance. And the trend now is toward dynamic automation of all of these different parameters. In days gone by, a lot of this was done a priori in trying to predict beforehand what your network needs and then set up the parameters that way. But with networks growing quickly and new base stations being added all the time, and perhaps even small base stations the size of Wi-Fi routers being added at unplanned locations, the tweaking of these parameters can no longer be done manually. So again, the trend is toward dynamic automation of these things. And obviously the operators want to respond more quickly to changing conditions. So you've got a base station here today, but then a building goes up the next day, and that changes completely the radio frequency characteristics around the base station. And so you'd like to adjust that, but you don't necessarily want a human involved in that process. So the operators are trying to save money on time-consuming and costly commissioning, monitoring, optimizing, and drive testing. That's actually, a thing that carriers do a lot, is they hire people to go out, in cars and walk around with mobile devices. Sometimes they have specialized vans to do this with all kinds of monitoring equipment, and they just drive around all over the place and try to measure where there are gaps in coverage or problems in coverage. To some degree, at least, this is being automated now, so that all of our devices are participating in the sort of ongoing optimization. So operators can, to some extent, minimize the cost for drive testing. The communication link between a base station and your device, your mobile device, is a very highly optimized and very sophisticated piece of communication. You have a very complex, highly optimized radio frequency link, which is edging ever closer to the Shannon capacity bounds for communication over a noisy channel. And that is done through advanced radio frequency modulation techniques and advanced channel coding, like forward error correction techniques, things like turbo codes or and things of that sort. There's also a sophisticated multi-user access and scheduling algorithms, so that all of the users in a given base station are sharing the frequency resources fairly, by some definition of fairly. And so because of this, because within a cell, the communication link is already highly optimized, the newer targets for optimizing the performance of the overall network are now between cells, or rather across dynamic clusters of nearby base stations. So, and that is the space that AirHop was concentrating in. So, roughly speaking, the old way of designing such a system would be to have a big server, and on this big server you have a big table, and in the big table you basically have one row for every base station that you're trying to optimize, And stored for each entry, for each base station, then you'd have a list of all of his neighbors, and in addition, all of the relevant state from the base station. So imagine this big table is in memory, and then you have a set of algorithms that run periodically over all of that data. And they make some decisions and then tell the base station, hey, change this or change that. So to summarize, the algorithms run globally over all the base stations in memory. Now, what are the problems with that? Quite obviously, it does not scale. So if your big, huge server handles n base stations, what happens with the n plus first? You know, you're a growing carrier, you're obviously going to be adding more base stations to accommodate your ever-increasing number of users and their, you know, ever-increasing demand for higher data rates. So you're going to be adding more base stations, and now this big server doesn't handle it. Clearly, the big server by itself is not resilient. What happens when it crashes? Yes, there are ways of standing up more big servers beside it, but then you have the additional problem of making your algorithms that just ran globally in memory work for the new big server that you just added. And it's not elastic for similar reasons. You can't easily add new machines to serve new capacity. So the key is to go from sort of a global perspective on these algorithms to a local perspective. So again, the key here is to structure the optimization algorithms so that they run as a cluster of fully distributable agents. And if you look at the transition from the old way to the new way, you can sort of see that now the base stations are speaking only to their local agent. And each of these local agents acts locally, of course, coordinating with its neighbors via message passing. And so the overall network optimization then appears as an emergent property of large number of these local agents acting simultaneously. And the term that we came up with at AirHop for these local agents is the cell optimization engine. And the name of the product that we created is called eSON. Again, SON is back to the telecom term for self-organizing network. And eSON is just our trade name for it. So with eSON, the inter-COE communication is, as I said, via message passing. And so what that means is that the COEs can run anywhere as long as they have communication capability. And so that gives them this location transparency property. That means they can run on any node. They can also potentially run on the base stations themselves if that's a deployment model that the carrier wants to use. Additional servers can easily be added because it's much easier to add a server and then start spinning up new COEs on it than it is to coordinate tricky ways of scaling the monolithic thing that I showed at the beginning. And then obviously if a single node crashes, then yes, you'll lose some, temporarily lose some COEs for the base stations that the crashed node was serving, but the base stations will re-register quickly with the system, and the COEs for them can be spun up somewhere else. Now, drilling in a little bit on this cell optimization engine. So as I said, there's one of these COE for short, one per cell. The inputs and outputs are via TCP socket with the base station. AirHop made a small, thin client that would actually be integrated with the base station in order to deliver the inputs that the COE requires, but also accept the responses or the output of the optimizing algorithms, and then deliver those to the base station so that they can take effect. The inputs are things like So on this base station here, you can see 5 devices currently connected. Those devices are actually continually monitoring their environment. So they're monitoring and reporting things like their signal to interference and noise ratio, and also the received signal strengths from the devices currently serving base station, but also from neighboring base stations that it may happen to see. So these things are continually being measured by the devices and sent to the base station, and then through AirHop's thin client and up to the COE. And once the COE has run some algorithms and decided what to do, then potential new values for certain operating parameters are pushed back down to the base station. Then the next step is that COEs for neighboring base stations, by some definition of neighboring, will coordinate in order to optimize across a group. So, and I'll talk a little bit more later about how that group is formed and what that group really means. And the net result of all this is, and I'm sure you can see where this is going, the COEs are actually Akka actors. So we're using Akka to implement most of this capability in eSON. And the tagline for AirHop eSON is always massively scalable, flexible deployment of SON algorithms for wireless networks. So here you can see N servers, and serving what could potentially be a very huge geographic area, depending on how big N is. Now, I mentioned that the topologies are dynamically discovered. What I mean by topologies is the connections between these COEs that need to be formed are, for the most part, dynamically discovered. And this is important because, again, the carrier can't necessarily pre-configure these things. In the old days, yes, they knew where they were going to put a base station, and they would establish some tables that said, okay, you're here, you have a neighbor that's over here, and then as soon as the base station came up, then they would get configured with these things. But again, the move now is to densify base station deployments and often make them much smaller, so there's no pre-planning possible. It's just not possible anymore. So the neighbor relationships between base stations need to be discovered automatically. And that happens, for example, if you have a device that's connected to a base station on the lower left, and if it happens to be close enough to a neighboring base station, he can detect that he's there and report that to the base station, but also to his COE, and then a connection can be formed between those two COEs. And now, when they run their optimization algorithms, they do so taking into account the input from the neighbor. And of course, this just shows two COEs and two cells, but the real picture is there's hundreds and thousands of these things, and they're forming these internal clusters of cooperating COEs where they need to cooperate. So again, it's mostly based on kind of geographic closeness or closeness of RF signal. I mean, geographic closeness doesn't tell the whole story, because there could be a big hill in the way or some big reflecting object that, even though two base stations are close together, they're actually not interfering neighbors, or their cell phones would not hand off from one to the other because there isn't really a visibility from a phone connected to one to a phone connected to the other. So again, that's another reason why these connections have to be dynamically discovered, because it's impossible to plan for all of the different things that can get in the way of the signal actually being received. So a word about the implementation. We actually use Akka cluster for this, and we use cluster sharding, which is extremely useful in this case because all the base stations have a unique ID, and we can use that unique ID in the COE clusters as well, so that a COE can talk to any other COE as long as he knows the unique ID for it. So that's extremely convenient. A couple of examples now of algorithms that were implemented, sort of optimizing algorithms that were implemented on this platform. One is known as mobility load balancing, and effectively what that means is you have some cells that are extremely loaded and nearby cells, neighboring cells that are not loaded at all. And if it's possible, you can actually shed some users from, some devices from the overloaded cell to the unloaded cell. And the way that's done is by manipulating the parameters that dictate how handover works. So handover is a relatively complicated process. So again, the device is continually measuring the signal strength he sees from his serving base station, but also the signal strengths from neighboring base stations, and signal quality as well. And when certain thresholds get crossed for long enough periods of time, then the device itself can initiate a handover to a neighboring target cell. So by manipulation of the parameters that control this, then the network can sort of force users to hand off to another cell. And that's what happens. In this case, you see that we went from 3 of the phones switched to the cell on the lower right. Let's see, yes. And so another algorithm that we implemented is called mobility robustness optimization. And it's related, but somehow different. The problem that's trying to be solved here is that if the network is not set up properly, there are some things that can go wrong when a device tries to hand over from one cell to another cell. For example, the device can think that he needs to hand off now, but he really should have handed off, or hand over, hand off, same thing. He really should have handed over a little bit later, and if he tries to do it too soon, then he may not actually have enough quality on the target cell to make the call uninterrupted, or make a seamless handover. The other problem can happen too, where he should have handed off a while ago, but he actually waited too long, and by the time he thinks he's going to start his handoff, it's too late, and the call's already dropped. So too early, too late can happen, and the way this algorithm essentially works is that the base station is keeping statistics on pairwise between itself and any other base station about how many too early and too late handoffs there were. And there's ways of measuring those things. And then the algorithm at the COE can make a decision after some period of time saying, look, we need to adjust again the handoff thresholds to improve this situation. Another algorithm that we implemented is known as transmit power optimization. And again, very basically, what happens is, I mentioned that oftentimes the neighboring base stations are actually using the same RF spectrum. And if you have a situation like the situation depicted here, you have a base station whose coverage area is in a sense too large, and he's impinging upon a neighboring base station's space. Now, of course, you want a little bit of overlap because otherwise your handoffs would always fail, but too much handoff because they're using the same frequency means that you're actually inducing interference. So it's a bit of a delicate balance. But what happens with this algorithm is if there are enough devices who are measuring their serving cell and some neighbor cell in some relative amount that's considered to be too great, and if there are enough of these, then the neighbor cell can be a candidate for reducing his transmit power. And so if that action is taken, then you can get a situation like this that is maybe more optimal. Of course, you can't reduce too much because, like I said, if these base stations reduce their coverage or their transmit power too much, then you'll have coverage holes which lead to drop calls. And just to mention a few other algorithms that we implemented on this platform, one of the most challenging algorithms was a coordinated intercell interference management algorithm. And this is an algorithm that actually has a little bit more of a real-time flavor than the other algorithms. The other algorithms can run, relatively slowly, order of seconds or maybe tens of seconds in some cases. This one actually operates quite a bit more quickly. Inputs to it are coming at roughly 40 milliseconds from the devices, and we generally try to take action in about 200 milliseconds. So I know to some people that seems like a very long time. In this world, it's a fairly short time. So the basics of this coordinated intercell interference algorithm is that in LTE, the radio frequency bandwidth is quite high by historical standards, so possibly 10 megahertz or 20 megahertz. That spectrum chunk is actually physically divided into subbands. So there's actually a frequency division technique happening within these frequency bands. And some frequency bands may be preferable to others in certain circumstances. There's an effect known as frequency selective fading that can occur just because of the nature of a certain cell and the environment it finds itself in, the buildings, the reflection, whatever. So it turns out that certain subbands within the overall allotted frequency band are better than others. And in very general terms, you would try to give users who need to send more data, allocate them to the better frequency subbands within the overall band. Now, on the other hand, it may be that you have a neighbor base station that has some of these frequency selective bands that are problematic, and so its users are all pushed off or prefer other subbands, whereas my base station doesn't have those problems on those frequency selective bands that the other one has, and so he could easily prefer to use those subbands, and in that way kind of like help the other base station and help to minimize interference. There's another algorithm that we have called physical cell identifier. There is a parameter that's used in LTE base stations called PCI, physical cell identifier, that's just an integer between 0 and 503, and that has to be unique for all neighbor base stations and all neighbor's neighbor base stations. If it's not, then problems happen, and in some cases, big problems. So again, in old days, these numbers used to be pre-planned, so the operators know where the towers are going to be and say, okay, you're 22 and you're 700 or 503. But that's not possible anymore because of the more dynamic nature of adding base stations. And so you want to be able to just plug in a base station and have it figure out what its PCI needs to be. And if there are collisions in PCI, then either it or neighboring base stations can make adjustments. So this is another thing that, another algorithm that AirHop has implemented. And the last one I'll mention is something called random access channel optimization. And the random access channel is actually the channel that is used from the device to the base station when it initially makes a connection to it. So it starts out with a small power level and sends a little test probe to the base station. And if he gets a response and he says, great, I'm done, I'm in there, I'm connected. If he doesn't get a response, then he waits a random amount of time and sends another probe at a slightly higher power level. The length of time that's waited, the sort of parameters of this exponential back-off, and the different power level steps are configurable parameters, and they can also be optimized to work better in certain circumstances and use fewer resources. So that's another algorithm that we implemented. So switching gears a little bit and just talk about a couple of the features of Akka that we used in this implementation. So there's a registration microservice, which is an extremely simple TCP server and backed by a load balancer. And base stations would send a registration message into the load balancer and then pick one of the registration microservices that's running. Once it receives it, then it will cause a COE to be created for that base station somewhere in the cluster. So again, these are all clustered microservices, so they're all part of the same Akka cluster. And then once the COE is up, then the base station can set up its permanent TCP socket connection between the base station and the COE. Again, this is the property of this microservice is that it can be independently scaled. So if you have a really huge cluster in a big data center that's servicing lots and lots of registrations, then you would tend to deploy more of these registration microservices. But if you have a smaller one, then you maybe only need 3 or 5 or something like that. Always, obviously, 3 or more because you want the resiliency. Another microservice that we've implemented is the API, RESTful API. And so that's done using Akka HTTP. There are a number of adjustable parameters for the eSON system itself. I'm not talking about all of the parameters related to the base station here. I'm talking about the parameters for the eSON optimizing algorithms themselves. And these can be controlled by an operator console or admin website, what have you, or CLI. So that's the purpose of these RESTful APIs. So again, a write would come in to a load balancer and then select one of the HTTP servers that's running. And again, you can independently scale these things and according to how big your deployment is. And obviously there's resilience. That's one of the reasons for doing it. The configuration parameters I just mentioned, as they come in to HTTP, we use Akka distributed data as the way to store those. So, and that's a really convenient feature of Akka that very easy to have distribution of these configuration parameters across the whole cluster. So an HTTP server will just simply write a config parameter for a given COE, given its ID, into Akka distributed data on its local node and let Akka distributed data distribute those. Now the COEs themselves, when they are created, they will subscribe to Akka distributed data with their ID, and then so when there's a change for that ID, they'll automatically be notified. So it's extremely convenient, and so as long as one node in the whole cluster is up, then that data is preserved. And if all nodes in the cluster go down, then we're using the durable storage backup of Akka distributed data that allows us to recover those parameters in that case. So extremely convenient feature. Another thing we're doing is some more microservices. There are some need for external interfaces to other parts of the carrier's network. And two in particular right now are a SOAP interface and some external RESTful calls that we have to make. So for the SOAP, we're using the Akka Camel package, and you can hook that up with Apache CXF, which provides RESTful and SOAP-based services. I don't use the RESTful part, just the SOAP. And for HTTP, we use Akka HTTP client. So the way this works is you stand up a few of these interface actors somewhere in your cluster, and then locally on each node you run a cluster-aware router that can reach the SOAP or HTTP interface. So that is very convenient as well. Works very nicely. The last thing I'll mention about our platform is, all of what you've seen is part of our product, part of AirHop's product today. What we've been working on recently is there's quite clearly lots and lots of data available, both quasi-real-time and lots of historical data available from all of the cells in a carrier's network, and it screams out for kind of big data and fast data techniques in order to gain useful insights from it. What we've done at AirHop is a proof of concept for sort of a fast data pipeline, and basically we're taking the mobile device telemetry, the signal to interference and noise ratios and signal strength measurements that I talked about earlier, and using Akka streams to push those off platform into something that looks a lot like Lightbend's emerging fast data platform, although that's not actually what we used here because it was just a simple proof of concept. So we stood up some local Kafka and Spark and wrote a few sort of proof of concept algorithms. One of the things, for example, that we're looking for a platform such as this to do for us is anomaly detection. So carriers often talk about a problem where a base station appears to be alive from network monitoring perspective. It's answering its health checks and what have you, but it's not actually serving any traffic for some reason. Its power amplifier has failed, although there's usually alarms for that, but something's gone wrong that isn't otherwise detectable. So what we've done is build a system or build an algorithm that uses sort of the historical trend of how much traffic a base station is carrying, and if it sees significant aberrations from that, then it can flag that base station as a potential sleeping cell, they call it, or cell outage. And did I mention that this proof of concept for this streaming fast data uses Akka streams to stream out this telemetry data, but it's also using the Akka streams Kafka or Reactive Kafka connector. And if you haven't looked at those things, they're pretty amazing, and with just a very little bit of code, you can do pretty cool stuff. So all this is implemented in Scala and Akka, yay. And the other thing about it is in production for about a year now in the world's largest LTE network, Reliance Jio in India. So they have 9 data centers, I think, currently spread out across the country, and so they're optimizing happily from each one of those 9. So that's all I have, and thank you so much, and I'll take any questions.
Hey, so how close are these distributed algorithms, which you're talking about? There's emergent, optimization properties rather than looking at it monolithically. How close are they to providing like Byzantine fault tolerance for the networks, or are they mostly just concerned with reacting to, changing conditions that will occur naturally and not in the face of like bad actors?
Yes, I understand. I think the best answer to that is that there's a long way to go. So they're nowhere near optimal. Again, within a cell, the communication theorists have spent decades optimizing how that link between a device and a base station operate. Between cells, there's a lot of room for improvement, especially, again, given that to fill in coverage hotspots or dead spots, really, or let's say you live out in a rural area and you're an AT&T customer, for example, and there's very little coverage. They'll give you something that looks like a Wi-Fi router and put it in your home, but they don't have the manpower to go and drive test that for you, so all the parameters need to be optimized. But there's still a long way to go. Our systems help a lot in most circumstances, but there's lots of room for improvement. All right, I think that's it. Thank you all very much.